Good morning. So hopefully most of you feel like you did pretty well on the quiz. It was not supposed to be hard, especially if you studied properly. I did notice that a lot of you did not sign in right at 8:30. And this time I actually allowed an extra 5 minutes, but I won't always do that. So if I say a quiz starts at 8:30, it means you need to be signed into the system at 8:30. It's not okay to show up at 8:32 or 8:34 because in the future that may mean you have less time for the quiz. Okay, so today we are continuing in chapter 4, which remember is UV-Vis molecular absorption spectroscopy. And I told you as we get into the instruments, you're always going to kind of see these three different parts. We'll talk about the instrument, and then we'll talk about the theory, and then we'll talk about application. So for this chapter, the instrument part of that is Beer's law, because that's what we're measuring. So last time, if you remember, we talked about the limitations to Beer's law, the conditions for Beer's law to be true. And we started to talk about the components, the parts of the instrument, and then we'll also need to talk about types of instruments. So today we're going to finish up the components and the type of instrument, and then we can move on to the theory. So last time when we looked at the components, remember all spectroscopy instruments have these same basic parts. So the first one's the light source. And remember, we talked about those last time. So you should now know the names of these light sources. By far, the two most common are what's called the tungsten halogen and the deuterium lamp. So tungsten halogen lamps, those are used mostly for visible light, and deuterium is used for UV. This source we mentioned, but it's a very strong, very intense source, so it's not commonly used for molecular spectroscopy. All right, then the wavelength selector, that's what we talked about in chapter 3, will either be filters or more likely a monochromator with a grating to select the wavelengths. Okay, the sample holder. We've talked about if you're in the UV, you're going to use quartz. If you're in the visible alone, you're going to use glass. Those are the most common. There are some plastics out there as well. And then if you're in UV-Vis, the whole range, then you would have to use quartz because glass and many plastics don't go down into the UV. All right, and then the detector. So we just talked about this a little bit at the end last time. We said the detector is going to be the thing that takes the light and turns that light into electrons so I can measure it. And it will do this either using something called the photoelectric effect or as a semiconductor. So there are many different kinds of detectors that we use in the UV-Vis. They're all the ones that take photons and turn them into current. And so notice there are 5. These 3 in bold we'll see are actually the most common or the most important for us. But we're going to go through them all quickly. We're not going to try to understand in detail how these work, but just very, very simply. And then what are the kind of some important properties about these in terms of how sensitive they are and their cost. Okay, so all of these detectors use one of two principles, okay, either the photoelectric effect. So this is where the light hits the detector and the energy of the light is higher than the energy holding the electron in the material. So the light will cause electrons to come out, and the number of electrons tell you about the amount of light. Okay, that's called the photoelectric effect. Some detectors will use that. others use what are called semiconductors. So you should know there are three kinds of materials: metals, which conduct easily, insulators that do not conduct, and then these things called semiconductors, which conduct under certain conditions. And we're not going to get into the theory, but just know that if you get light of the right energy, you get some electrons that come up and you get a flow that's proportional to light. Okay, so let's look at the specific detectors. So the first one's called a photovoltaic cell. Sometimes they're called photocells. And these are semiconductor sandwiches. Okay, it's a metal semiconductor metal sandwich. So notice we have a layer of silver, then selenium, which is the semiconductor, and iron. And so what happens is the light hits this, you get a flow of electrons, and that tells you how much light hits your detector. So these detectors are quite cheap. They're rugged, which means they're hard to break, but they're not very sensitive. You need a lot of light for these to work. Okay, so that's the first one. Not a very sensitive, not very common detector, the photocell or photovoltaic cell. All right, the next kind is called a phototube. And so what you have here is you have a cathode that's what we call photoemissive, okay, this word right here. And what that means is that when light of the right energy hits it, you get electrons. Okay, this is the photoelectric effect. So the electrons then will flow. There's a 90 volt, there's a power supply, and so this guy's at 90 volts. And so the electrons get attracted to that, and then we measure how much current. And again, the current tells me how many photons. So this detector looks like this. That's kind of a schematic picture of what it looks like. And this is a fairly popular common detector that's also pretty inexpensive. And you can change that electrode surface so that it will respond to different wavelengths of light. Okay? And so this just shows you some different types of metals that are used and where they're sensitive. So notice this 128 is made of gallium and arsenic, and that one has a nice response from the UV all the way up into the visible. This 117, made of different materials, that one, notice, is a more sensitive, but it's only really sensitive at in a small wavelength range. Okay, so that's the phototube. All right, the next detector is called a photomultiplier tube, and that's abbreviated PMT. So this is actually kind of like the phototube, except they've redesigned this so it's very, very sensitive detector. So this is good for very low levels of light. So you can continue to look at this. Hopefully you have your notes. I'm going to show you a picture of what's going on here. So again, we have this photoemissive cathode right here. So light comes in and out comes electrons. Now in the phototube, we just collected the electrons and that was it. But here we have a whole series of these things called dinodes. So the electron hits the dynode, and then at each dynode you get more electrons, not just one, you get 2 or 3 or 4. And then those all go to the next dynode. And then you get 2 or 3 or 4 for each of those. And then the next one, and then the next one. So by the time you get to the end, you have a very large signal. So if you go back here, notice that it says that it amplifies the signal maybe 10 to the 5th or 10 to the 7th. That means for one photon at the end, I get maybe 10 to the 7th electrons. So very big current. Could be as high as 10 to the 9th. Okay, so this increase in the signal is called a gain. So this kind of will show you in a picture, a moving picture, what this looks like. So here comes the light, out comes an electron, then they go to the dinodes. Each one makes more and more and more, so that by the time you get to the end, very large signal. Okay, so these PMTs, they're especially good at detecting UV light. they're extremely fast. They make these electrodes in just nanoseconds, so 10 to the minus 9 seconds. They're also very rugged. They're not easy to break. They last a long time. And they're linear over several orders of magnitude, which means they work from a very small amount of light to very large amounts of light. And they also have a pretty reasonable cost, about $100, so not too expensive for a detector. They do have what's called dark current. This means if there's no light, they still give you a signal because they're so sensitive. So that's called the dark current. So you actually have to cool them, usually to about minus 30 degrees, to make sure that you get a signal. You do have to be careful because if you get too much light, even the room light is enough to destroy them because they're so sensitive to light. Okay, so that's the PMT, photomultiplier tube. And then the next one is photodiodes. So this is a semiconductor detector. And for here, the current will only flow if you have light of the right energy. And so the current tells you how much light. It's proportional to light. These work from the UV all the way up into the IR, but they're not as sensitive as a PMT. The PMT is much more sensitive. They also have a very limited dynamic range. So we said the PMT has a very large dynamic range. For the photodiode, it's very small. So PMT, if we have the intensity versus concentration of light, very large range. The photodiode, very small range, and then it goes off from linear very badly. So based on this, we say, well, the PMT is more sensitive. The PMT has a bigger dynamic range. The PMT is cheaper. So why would we want this detector? Well, this detector has one very important property, and that is we can build it into arrays. Okay, so what does that mean? Well, if you remember when I talked about the spectroscopy experiment in general, we talked about in a typical experiment, we select one wavelength, and then the PMT will detect it. And then I need to select another wavelength, and the PMT will detect it. And then another one, and then another one, and then another one, and then another one. So we have to one by one select the wavelengths and then measure. Select, measure. And this is a slow process. This can take several minutes to get this spectrum. Okay, now I told you there's another way you could do this. You could get a detector that actually was able to look at everything at the same time. You spread out all the wavelengths, measure them all together, same time. Okay, so the photodiode, if you put them in an array, which means we put a whole bunch of photodiodes, one after another. Okay, we're going to make a whole row of photodiodes. Okay, it's called a photodiode array, PDA. And when we do this, now we can spread out the whole spectrum and measure it all at one time. And we can actually read thousands of wavelengths in less than a second. Okay, so it's a very quick way to look at everything at one time. Now, this is also important because we could use this for signal averaging. Remember, we talked about signal to noise. And we said if our signal to noise ratio is poor, one way we can improve it is to add a bunch of scans together. And then the signal will increase. Okay, so this one would look like this. These are actually pictures of what they look like. They look like these chips. So here I have my light source, and I shine it through the cell. I don't have to select the wavelengths because I'm going to look at all the wavelengths at the same time. And then my spectrum gets spread out on the detector. So all of this less than a second. Okay, so that's a very powerful way to look at spectrum. The problem is the resolution is not that great, but usually this resolution is okay for molecules. And also this kind of detector is fairly expensive. Okay, and then there's one last detector. This is called a charge coupled device, or CCD. So this is another semiconductor. And this is similar to the PDA, except this kind of detector is much more sensitive. This is just like the PMT, very, very sensitive. And it can read thousands of wavelengths all at the same time. You can read up to 5,000 wavelengths at the same time. So this is a very powerful detector, but it also is a very expensive detector. And for that reason, it's not very common for molecular spectroscopy, because we don't normally need a detector that's this high of resolution. Okay, so of these 5 detectors, this is sort of how they compare in terms of how sensitive they are and how expensive they are. So what do you need to know about these detectors? What you need to know is right here on this slide. You should know how they compare in terms of cost, how they compare in terms of sensitivity. So the photocells, those are the cheapest, but they're also not very sensitive, which means they're not very commonly used. Okay, then phototubes are next, PMT, PDA, CCD. Okay, for sensitivity, phototubes are second, PDA is third, and PMT and CCD are the same. So these 3 in bold are the most common for molecular spectroscopy. Okay, this last one is a very good detector, and it's used commonly for emission spectroscopy that we won't talk about in this class. Okay, so for us, really the most important detectors are these 3. All right, so you should know how sensitive they are. You should know their cost. The other thing you should know is which ones are array detectors. And that means I can measure all the wavelengths at the same time. Okay, so that's the detectors. So if we go back to this picture of this instrument, this is a common, inexpensive instrument that you might find in the lab. And this is what it would look like on the outside, but notice what it looks like on the inside. So notice it has these parts we're talking about. We said the first one was the source. So right here, this is the source. Notice the source is a tungsten lamp. Now, what does that tell you about this instrument? What kind of light can we study with this instrument? Okay, tungsten lamp, visible light. All right, then notice from 2, goes out here to 4 is the grading and some other stuff, but from 2 to 7, that's your monochromator. That's what's going to select your wavelength. All right, then you have your sample holder. This is visible, so that's probably going to be glass. It's probably going to be a test tube, actually. And then your detector. So notice the detector is that photo tube. Okay, that's that kind of relatively cheap detector, but still not super sensitive, but for just common, simple experiments, it's sensitive enough. Okay, so those are the components of an instrument. All right, so we've looked at all of those. So just kind of to summarize the sources, the 2 most important, again, tungsten halogen and deuterium. Okay, we've talked about the sample holder. We talked about this in chapter 3. And then the detectors, the 3 most important for this kind of instrument, UV vis, molecular absorption, are these: phototube, PMT, and PDA. Okay, so PMT when you need really sensitive measurements, PDA when you need to get the whole spectrum at one time. All right, so lastly, for the instrument part, we want to look at the different types of instruments. There are 3 instrument types, one that's called a single beam, one that's called a double beam, and then something that's called multi-channel. All right, so for a single beam, notice I have my source and my monochromator, and then my cell and my detector. Now, remember, in an absorption measurement, we need to measure P and P0. And we talked about at the beginning of this chapter that P0 is actually P of my solvent. And remember, your solvent is your blank, your reference. Okay, and then we need to measure P. P is the P of your solution, the P after it goes through your cell. So that's P of your sample. So that's the measurement. I need P from my sample and P from a blank, and then I can calculate transmittance. So with a single beam instrument, what you would do is you would take your little cuvette and you would fill it up with solvent, your blank, and you would put it in here and you would get a number, okay, and that's P0. Then you're going to take that, dump it out, put your sample in. Now you're going to measure P for your sample, that's P, okay, and now you can calculate absorbance for your sample. Now, this was the first kind of instrument that was developed, but this kind of instrument had a big problem, okay, something called drift. So drift is a change in your baseline, a change in your reference with time. And there are several reasons why your baseline could change with time. One is, the most common is that your source intensity changes with time. You know, sometimes you turn it on and then as it's on longer, the source gets brighter. Or if your source is getting old, it might start to get weaker with time. Okay, you can also get drift if the monochromator is changing, it's heating or cooling with time or vibrating, or if the detector response is changing with time. And this can happen as your detector is getting older, or if the current, the voltage to your detector is changing a little bit, that changes its response. So any of these changes in your instrument can cause this thing called drift. So here's a very extreme example of drift. So notice, say I come here in the morning and I measure my baseline, and then I measure my signal. Okay, and then I come back later in the afternoon, and what I don't know is that my instrument is drifting. Something is changing in the instrument, so that now my baseline is way up here. But if I don't measure the baseline again, I just assume, well, I measured it this morning, it'll be the same. So I think my baseline is here. Notice you're going to have a huge error. You're going to have a big problem with your measurement. So this is something we have to think about. How can we fix this problem? So there's several things you can do. One is you keep checking the light intensity. You know, you check, because usually the problem is the light changing. So you check the light intensity every time you make a measurement. Another thing is you have a standard. And a standard should always give you the same signal. So you measure the standard in the morning, and then you measure it in the afternoon to make sure nothing's changed. Another way, keep checking the background. You know, every time you measure a new sample, check the background to make sure it's not changed. And then the final way you can deal with this is something called double beam optics. So these are instruments that look like this, and there's two different ways to do it. So let's look at the top one first. So again, I have my source, I have my monochromator, and now what I'm going to do is I'm going to take the light and I'm going to split it so that half the light goes to my reference, my blank, and half the light goes to my sample. And then I have two detectors that are matched that give you the same response. And what you're going to do then is compare the signal from the reference to the signal with the sample. And these are made at exactly the same time. So if that reference changes, you'll always know, because you're always measuring sample and reference exactly together. Okay, so that's called in space. Now, this is a little bit more expensive because you have to have two detectors. So a more common way is to do it the second way, which is called in time. So again, my source goes through the monochromator, and now I'm going to use something called a chopper. So what this does is it's going to split the light alternately. So the light will go through the reference if it goes through this way, and then if it doesn't go through the reference, then it will go through the sample. And then they meet again at the detector. So what you get is something that looks like this. Okay, so the light is going sample, reference, sample, reference, sample, reference, sample, reference, sample, reference, and then they go off to the detector. So again, you're measuring the sample and the reference not at exactly the same time, but very close. So again, if there's any change in the background, you'll see it here because you're constantly measuring sample, reference, sample, reference, sample, reference. Okay, so that's double beam optics. Here's again just showing you the same thing with it not moving. Okay, so this will compensate for if there's changes in your source, if there's changes in the source at different wavelengths. You know, you have different intensities at different wavelengths. This will fix that problem. If the detector is changing with time, this will fix that problem. So this makes reading the spectrum and the background always at the same time much easier. This is a very convenient way. And when this was developed, it actually made this method a much more powerful and useful method. Okay, because before this, with the single beam, you have to every time measure the reference and take the whole spectrum, then measure your sample, take the whole spectrum, and then every time. But now these are always done together. So this double beam instruments are more common and more useful. Okay, and then before I get to the third type, I should mention for these double beam instruments, okay, where we're measuring sample, reference, you need two cells, okay, one for the reference, one for the sample. And it's very important that the absorbance of these two cells be as close to each other as possible. So there are some cells that you can buy. They're called matched cells. And these are cells that should have very close absorbance. Now you actually buy these. You buy them as a set. So the people that sell cells, they've done a lot of work to make sure the absorbance of these two cells is almost exactly the same. Okay. Now they always do vary a little bit. So you still have to, first thing you do is run a background of these two empty cells versus each other and subtract that from everything. Okay, so these matched cells are something that you have to use. Now, matched cells are expensive. If you just buy one cell, it's much cheaper than buying these two matched cells because these cells have been specifically chosen to be the same. So if you're ever using matched cells, you want to be really careful with them because if you break them or damage them, they're going to be expensive to replace. Okay, now we'll look at the last type of instrument. These are what we call multi-channel. And these are no longer new. They've been around since the 1980s, but this is where we're going to use that PDA detector. So remember, what this detector can do is we can measure all the wavelengths of light at the same time. And we can get the whole spectrum in less than a second. And this is very common if you're needing to study the kinetics of reactions, or if it's a detector for a chromatographic system where you need to measure everything very quickly. Again, this kind of detector is going to be a bit more expensive. So these instruments that have this are more expensive, and the resolution's not great, but usually for most biological samples, it's good enough for what we need. All right, so this is what this looks like. My source goes through the sample. Now notice There's no wavelength selector here. And then we're just going to have a grating to spread out the whole spectrum right on that detector. And so this one, notice you're actually measuring the spectrum every 5 seconds. You get a new spectrum. And so we can actually watch things coming off a separation column as we're doing it. So very powerful detector if this is what you need. Okay, just as we look at this, is this a double beam or a single beam instrument? Okay, well, notice it's single beam. And I just finished saying how many problems the single beam had, because of this drift. Okay, now is that going to be a problem here? Is drift a problem here? Usually not, because these measurements are so fast, the instrument really doesn't have time to drift. Okay, so it is single beam, but usually we don't have to worry much about drift because these are very fast measurements. Okay, so we've now looked at the different types of instruments, the single beam, double beam, and multi-channel. So if you ever use this instrument, you have used it in the lab, or you later are doing research or other things where you need to do a UV vis absorbance, you will see there's all kinds of instruments. And they might have different names, but they all have those same basic parts. Now, just a quick note about the names. If we use a filter to select the wavelength, then we call the instrument a photometer. If we use a grating or a prism, usually gratings, we use a grating to select a wavelength, then we call it a spectrophotometer. Okay, so they both give us absorption, but filter selects the wavelength. It's called photometer, grating spectrophotometer. Okay, now these different instruments, there are all kinds of varieties and options. Some only measure visible, some measure the whole UV vis. Some will be single beam, some will be double beam, some will be multi-channel. When you buy an instrument, they'll tell you, what is the bandwidth for that monochromator? What kind of resolution does it have? What kind of wavelength accuracy? How much stray light? Okay, these are all things that you can find out about an instrument that you're using. Okay, so we have now looked at the instrument, which included looking at Beer's law. We've looked at the different parts of the instrument, and then we saw the 3 types of instrument. Okay, now in part 2, we're going to be looking more at the theory of how we use this. So first we're going to look at the molar absorptivities a little bit closer, and then we'll look at types of transitions that we measure, and then the factors that affect band position. But we won't do that all today. We'll get started a little bit today, but we'll have to finish this next time. Okay, so let's go ahead and go back to the theory. So we're looking at molecular absorption spectroscopy, which again means that I have something in a ground state, it's absorbing light and going to an excited state. Now on the quiz, I asked you what kind of transitions do we have in molecules? And you should have answered that question. And so for molecular absorbance spectroscopy, what kind of transition are we talking about here? Well, UV vis light has enough energy to excite electronic transitions. And specifically, what we're talking about is exciting the outermost electrons. We have several names for those. We can call them outer shell electrons, or bonding electrons, or valence electrons. But those are the things that are actually absorbing this light and going to a higher energy level. Okay, and we know that this absorption is governed by Beer's law, okay, where the absorbance is equal to this guy, molar absorptivity times path length times concentration. So let's look at molar absorptivity again. Okay, and everything I'm going to say is the same. Sometimes we use A. Remember, we use this symbol if the units is molarity. If the unit for concentration is something different, then we use this, okay? But it's the same idea, just different units. So if we're talking about absorptivities, what is that? Well, remember, it's a measure of how much radiation will be absorbed by a given molecule at a given wavelength. So this number is a constant. It's a physical property of a molecule. So I can take any molecule and I can tell you its absorptivity. And what I'm telling you is for that molecule at that wavelength, I can give you a number. Okay, this molar absorptivity. If I change the wavelength, this number changes. If I change the molecule, this number definitely changes. Okay, so these molar absorptivities, they're determined by the molecule, by how strongly it absorbs and how likely it is to absorb. And these numbers can go anywhere from 0. Okay, a molar absorptivity of 0 means it does not absorb, all the way up to 10 to the 6th. Okay, so that can be pretty big numbers. So if that number is bigger than 10 to the 4th, then we say that's a very strong transition. Okay, that molecule strongly absorbs that wavelength of light. If it's less than 10 to the 3, then that's a weak absorption of light. And if the number is less than 1,000, 0 to 1,000, these are what we call forbidden transitions. All right, now we have to talk a little bit about what do we mean by forbidden. Okay, so normally if I say something's forbidden, okay, that means it's not allowed. You shouldn't do that. But let me ask you a question. If something is forbidden, can you do it? Well, you can. You shouldn't, but you can. Okay, so when we say a transition is forbidden, that does not mean it does not happen. Okay, forbidden transitions happen all the time. Okay, what forbidden transitions mean these are very weak transitions. The absorption of light is very weak, and the absorption of light is less probable. So if we have a strong absorption, then the molecule really wants to absorb that, and usually will. But if it's a forbidden transition, that means it's less likely that it will absorb. It still does absorb, but these are weak. Okay, so forbidden transitions happen. Okay. All right. Now, usually when we talk about molar absorptivities, I talk about the maximum molar absorptivity. And of course, that happens at lambda max. So if I have my spectrum, remember spectrum is, in this case, we're looking at absorbance versus wavelength. So I measure my spectrum and I get this peak. So usually we want to look at this number right here. Okay, this is lambda max. And we will use the molar absorptivity at that number. Now, why do we use lambda max? Okay, why do we use lambda max? Remember, we talked about this last time. There are 2 reasons, and you must know these 2 reasons. Okay, you must know these 2 reasons. So, first reason we always use lambda max is maximum sensitivity. This is where my signal is the highest, up here at lambda max. Okay, so this will give me the highest signal. That's the first reason. And the second reason, remember we talked about for Beer's law, I need monochromatic light. I need 1 wavelength. Okay, but I never have 1 wavelength. Remember we talked about that I actually get a band of light. So we want to make, we're going to get this band of light from the monochromator or the filter. And so I measure up there at the top because that means the molar absorptivity at this value and the molar absorptivity at this value should be pretty close to the same so that we get a linear calibration curve. Okay, so the second reason I always use lambda max is so that I will follow Beer's law. Okay, so that's molar absorptivities. All right, so next, the type of electronic transitions that we have. So there are 3 different types of electronic transitions that we can talk about for absorbing UV vis light. And remember, all of these are the valence electrons, the outer electrons. So the first type are those things that we call pi, sigma, and n electrons. So these are basically absorption in organic molecules. Okay, the second type we'll talk about are D and F electrons. This will be absorption in inorganic molecules. And then finally, there's some charge transfer. And this is often changing electrons between inorganic and organic. So we'll look at both of those. But we will spend most of our time on this one, the organic, the pi, sigma, and n electrons. So let's just review what that is. And again, all of these are those valence bonding electrons. So all organic molecules can absorb light because they all have valence electrons. And so we talk about these 3 kinds of electrons. So the first one are the electrons that are in a single bond. And all organic molecules have single bonds. So these are called sigma bonds. And then we can talk about electrons in double or triple bonds. These are called pi bonds. And then finally, we can talk about the electrons that are not involved in bonding, the lone pair. So these are the N electrons. So these will be for molecules that have things like N or O or S, chlorine, all of these have that lone pair of electrons. So to just give you an example, here is a molecule that has these 3 types. So we said the first type was the sigma electrons. That's single bonds. So you see there are single bonds, here and one of these bonds. So if we say a sigma electron is absorbing light, those are those electrons in the single bonds. Okay, then we can talk about pi electrons. Okay, for this you need a double or triple bond. So that would be, for instance, this pair of, well, I guess in this picture they're saying this one, but so that second set of electrons. Or if you have, one of those is a sigma, the other 2 are pi. So it's those electrons that are absorbing. And then finally, the N electrons, that's the lone pair. So that would be like these electrons, or those. Those are absorbing the light from those. Okay, so starting next time then, we will start looking at these transitions of the sigma and pi and N electrons. Okay, so next time we will be finishing chapter 4 for next time. You do not have any homework this week to turn in to me, but in this class you always have homework. So your homework is to be reviewing this. You need to look at the questions in the book. The next quiz will be on chapter 4 and 5, and there's actually no math. There's no calculations for those. So all of the questions will be general information, and they'll be like the short answer, true, false, multiple choice. So there's still a lot of information. So you should begin looking at chapter 4, looking at the questions that I've talked about. Okay, so that will be it for today. I'm going to go ahead and stop there. If there are any questions, or anything you need to discuss with me, you can stay around. But the rest of